you can see that how the port address of output of this, and each dedicated pins are connected to the controller part. So what next you can see, they are using wishbone. This WB stand for wishbone. You remember for buses we had seen the standard one, wishbone bus. So this is a wishbone bus connected, and you already saw the 8 bits of wishbone bus. That was for address, data, input, data, output, write, enable, strobe, cycle, acknowledgement, and this is, you see, interrupt request, and this is interrupt acknowledgement. ITAA is interrupt acknowledgement. So you can see how many bits are there. So you can see 8 bits are there. So this 8 bits are using wishbone bus and connecting Gumnut processor with the I2C controller, temperature controller device it is connecting. So this is just to the controller with wishbone bus with Gumnut processor, which is being interfaced with this analog device AD7414. So what you can see, the output of this, so this dashed block, what you can see, this is the embedded system. This is the embedded system which is having controller, wishbone bus and Gumnut processor embedded in it. So all this is part of one system. This is outside this embedded system. This is your interface IO device. This is your IO device. So what you can see, they are making it, they are connecting the voltage source, and if it is above certain level, this is one LED connected to it. So this is with alert. So if the temperature is beyond a certain range, this alert becomes high, and this high will make, as you can see, this is active low, anode, common anode connected. So this must be active low output alert. So once the temperature goes beyond that range, they will show that with this alert bit, alert connection here, and they have not shown here, but with the connection you can make out that it is active low output. So whenever it is the temperature is going beyond that and you want to alert, this will make it 0 and make the connection in such a way that current start flowing, and this LED will glow and it will show that there is a alert signal when the temperature has gone beyond the certain specified range. So this is how they are trying to show the temperature sensor using the I2C bus. If you remember, yesterday I told for I2C bus, the important thing is that they are having 2 wires flowing, one for the signal and another one for clock. So it always requires 2 signal, one for NRZ coded serial data and other for clock. So that is why that can be seen here, that here separate clock signal is there, and this is the data bus and the clock signal. So this is about I2C example for temperature sensor. Next we will see the IO software. Now you have seen that IO devices interact with the real physical world, and the embedded software need to be able to respond to events when they occur or to cause events at the right time. So this is a real-time behavior, which is the basic difference between an embedded software and a program for general purpose computer. You have seen general purpose computer means your desktop or your laptop. In that, most of the IO device for checking the real-time environment will not be there. But embedded software, any such embedded software device, maybe in your AC or any other system, it is different because it has many interface devices connected to it, which will be checking the real-time environment. So that is the main difference between embedded software and a general purpose computer. So embedded software needs to be able to detect when any event occurs so that it can react to the changed surrounding, or we call it as event when there is a change in the surrounding. And this this embedded software along with its IO software, it needs to be able to keep track of time so that it can perform actions at specific time or at regular intervals. So this is how it is done. It is done using a IO software. So IO software will be of various type. We will see one by one each one of it. So IO software, it uses input and output instructions to access any IO controller register. If you remember, when I taught about controller, that time I told that IO controller will be uh, uh, the IO controller will be connected to the specific register in the processor, so that any uh, input value data will come and store in this IO controller register only. So IO devices, it interacts with the physical world, that I already told. So the software which is um, embedded in our embedded system, this software must respond to events when they occur, and it should be able to schedule activity for the specific time or at regular interval. Now we will see what do you mean by specific time and what do you mean by regular interval. And the most important thing, it is real time behavior. As environment changes, that way IO devices output input changes. That way only it has to interface with the your IO controller, and in that your IO software will be loaded. Now let us see one by one each type. The first one is polling. You all know what is polling. Polling means one by one it will be reading the IO status. So polling software, it repeatedly reads IO status to see if an event has occurred. So for example, if you remember your keypad controller, the first thing what we had seen. So keypad controller, what we had seen in the program also, with the specific clock frequency, it used to keep on checking all the row wires to see whether any key is pressed or not. That was an example of polling. So this thing what you had made that time, to make it check regularly one after the other, just going on around and checking and coming back, again go on around, check, come back. This is polling. So software repeatedly reads IO status to see if an event has occurred, and if event has occurred, it is supposed to perform the required action. Now what you saw in keypad controller, there was only one keypad controller and we were checking the rows of that keypad. But if you have more than one controller, if you have multiple controller, one for keypad, one for something else, in that case also software executes a polling loop, and it will check controllers in turn by turn. Every controller will get its turn when the polling software will come and check whether any event has occurred or not. So what is the advantage of polling software? It is simple. It is a simple IO controller. And what is the disadvantage? The disadvantage is it keeps on checking even when event has not occurred. So processor is continuously busy and it consumes more power. This is one basic disadvantage. Other disadvantage is there will be a delay in dealing with an event if the processor is busy with any other event. For example, this polling thing, if any event has occurred but the polling scheduled time has not come for that, also if the processor is busy in any other event, it will delay this polling checking. This will delay. So that is another disadvantage. So this is most basic one, starting one. And next, after this polling, you have interrupts. You all know what is interrupt because you have already studied the course on microprocessor, microcontroller. So you know what is interrupt. Now how it is used in real world with embedded system, you will get to know today. Now, interrupts means what? The IO controller notifies processor when an event occur. So it will not go on checking. Interrupt will be created by the device to processor through IO controller. So IO controller will notify the processor, and processor, what it will do? It will interrupt whatever it was doing. And how does it interrupt? It will whatever it was doing, that also should not be lost because of this interrupt. So whatever it was doing, that address will be stored in the program counter. I hope you all remember what is program counter. Program counter will always keep the address of the current process happening in the processor. So when interrupts the processor will store the current work in the program counter, and it will go and attend the interrupt. After completing the interrupt service routine, it will come back and it will resume its interrupted task. And how it will resume? It will resume by checking in the program counter what was stored, what I was doing. So it will check from there and continue or resumes its interrupted task. And if it was not doing any work before getting interrupted by an IO controller, it can simply enter in a low powered standby mode. So this is the basic principle of a interrupt working. So if you have more than one IO controller, what will happen? Then the system will prioritize interrupt request. So for example, if I have 5 devices connected, I have 5 IO controller. So the processor will prioritize these 5 devices. So you know this overriding the interrupt request and all. So most high priority interrupt will be taken care first, and a lower priority will made to wait. So this also comes in this, that some system prioritize interrupt request, and it will allow higher priority event to interrupt service of lower priority event. So that means what? Now you imagine processor is working, interrupt request came from a low priority, it will start working on that. But if a high priority event occur, it will interrupt this low priority interrupt service routine, and it will store that also in a different counter. So there will be many program counter in such cases. Program counter for main processor, and also to store the event for a lower priority interrupt request. It will go and execute higher priority event, then come back to lower priority event with the IO controller interrupt. Then it will go back to the main processor and resume that task or enter in low power standby. So this is the most common way to synchronize embedded software with IO events. So we call it starts executing its interrupt handler, and or we can call it as interrupt service routine to respond to any interrupt. So this is the method of working with interrupts through IO controller. Now, interrupt mechanism. This I have already explained. We can just see again what happens in interrupt mechanism. Interrupt request signal will be enabled. You remember it is IREQ. Interrupt request signal will be enabled. And what does it mean? It means the disabling or enabling of interrupt, and processor can execute critical region, and processor, whatever work it was doing, will be saved. So it is called as save processor state on an interrupt. It is saved by saving the address in program counter, so that interrupt task can be resumed. Next, what is the step? On interrupt, it will disable further other interrupt. It is disabling further interrupt means what? If it is working for a high priority interrupt, because a processor may not have capacity of handling so many interrupt together, because the number of program counters are also limited. So that is why when it is interrupt and it is high priority interrupt, then it will disable further interrupt, and it will keep on working on that, and till that time processor will have its saved state in the program counter. For the interrupt handler code, what happens? It will have the address of handler or index into the table of handler address. What is this handler and handler address? It is the interrupt, the interrupt address. It will be working on that interrupt service routine. For that, this handler code will be used for that interrupt event. So once that is done, what will happen? Instruction to return from handler. Handler is your interrupt service routine handler. So it will come back from that after finishing that task, and it will restore saved state. What is this saved state? Saved state is the processor state where it was working when it was interrupted. So when interrupt mechanism is over, it will come back to its processor saved state and it will continue working on that. So this is interrupt mechanism. You should know this complete process. Now Gumnut interrupt mechanism. You will see one example also with this. So this is what I told you. It is interrupt request signal. Interrupt request signal is int_req. Disable interrupt. This is DISI, or enable interrupt signal. ENAI, enable interrupt signal. On interrupt, what all happens? It will save its program counter, Z register and C register as a special register. It will save the special register, and on interrupt, further interrupts are disabled. That is how this DISI will be used. Further interrupts will be disabled, and handler code starts at address 1. So this is for your interrupt handler code. It is not your main processor handler code. Okay, please don't confuse. So a handler code starts at address 1, and Gumnut will set its PC to 1. This is for interrupt, not for main. So once it is done, once your interrupt is acknowledged, executed, finished, then return instruction will come. So return instruction will be return from the interrupt. So then what will happen? It will restore its program counter and other special register when it re-enables and re-enables all other interrupts. So this is the interrupt mechanism of Gumnut processor. You are doing all the things related to Gumnut processor in this module. Now interrupt acknowledgement. It is again an important thing that you have to acknowledge interrupt. So what happens in this? It will tell the controller when it receives the interrupt request. So process may not respond immediately, but it can tell controller that when I will be doing it, and also it will acknowledge interrupt IO controller that your interrupt is acknowledged. Processor got to know that you are asking for to acknowledge an interrupt event. So processor will be telling to the controller by acknowledging the interrupt given by the IO controller. So after that, the controller can then deactivate this request, because otherwise what will happen? It will multiple interrupts will come for one event only. For example, temperature has become low. It want to tell to the interrupt to the processor that temperature has become low, you do something. So if you don't acknowledge, IO controller will keep on giving many interrupts for that one event only. So as soon as IO controller gives an interrupt request, the processor has to give interrupt acknowledgement, so that it understands that now processor will be doing my work, and it keeps quiet till the processor comes and do. So that is how processor acknowledges the request. So interrupt underscore acknowledgement is the signal on Gumnut. It will be telling to the IO controller. Another alternative for it is, there is a status register in a processor. So processor can update its status register, and IO controller can read the status register to understand that processor has acknowledged my request. Okay, now whatever you have understood with all this, you will be able to understand it further with this sensor controller example. Now this sensor controller example, in this example, I will tell you the question. The question is, design an input controller that has 8-bit binary coded input from a sensor. Okay, please understand. Design an input controller that has 8-bit binary coded input from a sensor. This value can be read from a 8-bit input register. You know, na, whenever any data is read from a sensor, it is stored in a input register. The controller should interrupt the embedded Gumnut core when the input value changes. The controller is the only interrupt source in the system. Why they are telling this? Because it has only one IO controller and there is no other IO controller connected to the Gumnut core. So now you should understand what is happening. See this diagram. It has to see the change in the sensor value. It has to see the change in the sensor value means what? It should know what was the previous value also, because we need to detect the change in this sensor. If we need to detect the change in the sensor, we also should know what was the previous value. And what we will do, we will keep on comparing the previous value to the current value. Then we will get to know if any change has happened. And if there is a change, then we will set an interrupt request. So how it is done? You see this diagram carefully. This is a D flip-flop. So your sensor input data is coming from here. So this D latch or D flip-flop, what it will do? It will store your sensor input signal for 1 clock cycle. So whatever your sensor input signal is coming after 1 clock cycle will be seen here. And another clock cycle it will be seen here. So now I have a inequality check here. So what it does, it will check, this is the previous state of the sensor and this is the current state of the sensor. So it keeps on checking the previous state and current state. If previous state and current state is same, then this will output will be 0. That means there is no change happened in the sensor. But if the previous state and the current state is different, inequality happens and then this bit will become high. So if this bit becomes high means what? A event has occurred. Sensor has got some value changed. So this is identifying the change in the sensor value. So it should interrupt the processor. So what will happen now? This is your high value. Now you understand till here. Current state of sensor, previous state of sensor is compared. If it is not equal, this bit become high and here you get a high. And because it is a OR gate, with one high you get a high here. You get a high here. And what is this other wire connected? It is interrupt acknowledgement. So you know that interrupt acknowledgement will become high only if the processor checks your interrupt request and it makes it high. Until you give interrupt request, till that time by default it will be 0 only. So this is 0. Interrupt acknowledgement is 0 by default. So it will be always 0 by default. So it will be 1 here. So as the event occurs, this becomes 1. This is already 1. So this 1 goes to this D flip-flop and this 1 will go to this interrupt request. So this interrupt request, what will happen? This interrupt request will go to the processor. This interrupt request will go to the processor and it is fed back to this, and this will remain high. You please see this carefully. This will remain high till when? Till you have your event being occurred here. Who can make this low? It can be made low only if this interrupt request signal is accepted by the processor, acknowledged by the processor. When this interrupt request is acknowledged by the processor, processor will give interrupt acknowledgement as high. So you see here, this interrupt acknowledgement high will come from the processor. When this becomes high, when interrupt acknowledgement becomes high, then what happens? This becomes 0. And when processor has acknowledged your request with this 0 here, this will become 0 and interrupt request will become 0. This means what? IO controller has notified the processor to do work, and processor has acknowledged, and now this IO controller will keep quiet and will give the control to processor to take care of this interrupt event. What else is connected in this circuit is, of course, your reset and clock is there. And I hope you all remember your cycle input and strobe input. These two input makes the processor work. I hope you remember from Gumnut processor. So once these two are also high, the acknowledgement will go, and this acknowledgement says that processor is in work. This will make the processor work. So this is about sensor controller. You are supposed to understand the program related to this also. So for program, I will share the another screen. Okay, this is the program. I have told you the logic of this. I have told you the logic of this, and now you should see the program of this. So whatever signals you saw there, all that signal you will see here also. This is the module of sensor controller. You have your clock input, reset input, cycle input, and strobe input. So you know the cycle and strobe is for the processor. This will come from the processor, and this is acknowledgement output. So this module of sensor controller, you know, this diagram you have already understood. What is this? This is data output. Data output. What is this? This is here. You can see here. What is data output? Data output is this. Output interrupt request register is taken as output register. Interrupt acknowledgement is this one. And your sensor input data is here. And it will also store your previous sensor input data also, so that it can compare. This is an important thing. Please understand carefully. You should understand this program also. Now you see what is happening at the positive edge of this. If reset is high, nothing will happen. Previous data and the data output will be all 0. If reset is not high, then what will happen? In data output, with one clock cycle, data output will go to previous data and sensor input will go to this data. So this data and this previous data only is compared. So this happens at one clock cycle, sensor input data will go to data output. In next clock cycle, data output will be going to previous data. So this is compared. Next, what happens? Interrupt state. In interrupt state, what is happening? If reset is high, of course, it will be 0, nothing will happen. But if it is not high, if it is not in reset mode, interrupt request will be taken care. So interrupt request, you can see here, if data output, this data output and the previous data, if both are not equal, interrupt request will be made high. Interrupt request will be made high. Once you get the interrupt acknowledgement from the processor, so if interrupt acknowledgement becomes high, that time you will have to make your interrupt request as 0. Why? Because processor has acknowledged, so your interrupt request will become 0. So this is about the requesting the processor and acknowledging it. And this, anyway, you know, this is for the this part when things are in work, cycle input and strobe input, acknowledgement output will be high, telling that this is under work. So this is about your program. Now this part takes care of your basic interrupt mechanism and how it is taken care by the processor and the interrupt service handling routine.